Okay guys, right now I'm going to solve the quiz version B from class on Friday. You see the first question asks you to write the dual of an LP. So again, a number of ways you could sort of go about this to wind up at the same answer, but the first thing I'll always do is say the dual of a max problem is a min problem. Then I always identify how many decision variables I need. There's going to be a decision variable in the dual associated with each constraint in the primal. So you can sort of write them out. There'll be y1 and y2. Okay. The coefficients in the objective function of the dual will be the right-hand sides in the primal. So my dual objective function is going to be minimized 10y1 plus 8y2. Okay. Now, as for the number of constraints in the dual, it's going to be equal to the number of decision variables in the primal. So I've got two decision variables in the primal, so I'm going to have two constraints in the dual. And the right-hand sides of those constraints are going to be my objective function coefficients in the primal. So my right-hand sides of my dual, I'm going to have 2 and 1. Okay. The types of the constraints in the dual are related to the types of variables in the primal. So specifically, the first constraint is related to this decision variable. This decision variable x1 in the primal is an unrestricted and signed variable, which we said is corresponding to an equal to constraint in a dual. So that means my first constraint is going to be equal to. The type of my second constraint is related to the type of my second variable in the primal. This is x2 less than or equal to 0. That's a non-positive, which we call an opposite type, or you could think of it as a non-normal decision variable. Okay. A non-normal decision variable or an opposite decision variable in the primal is associated with an opposite type constraint in the dual. For a min problem, an opposite type constraint is a less than or equal to constraint. Okay. The next thing I tend to write out is the A matrix in the dual. This is just the A transform matrix from the primal. So what I have is y1 plus 3y2 equal to. So you see that first row in the dual A matrix, it was the first column in the primal A matrix. And then the second will be y1 minus 2 y2 less than or equal to 1. Alright, the only thing left to do is figure out what are my decision variable types in the dual. So what I mean by that is I know y1 will have some type and y2 will have some type, and by the type we're talking about the relationship with 0. And the types of my decision variables in the dual are related to the types of constraints in the primal. Okay, so here I said y1 is associated with this constraint. This was a less than or equal to constraint. For a maximized problem, we said that's a normal type constraint. So y1 is going to be a normal type decision variable in the dual. And you see y2 is also associated with a less than or equal to constraint. That's a normal constraint, so y2 is going to be a normal decision variable, which is a normal decision variable is always greater than or equal to decision variable, whether you're talking about a min or max problem. So that's how we wrote the dual. The second problem gave you a graph of an LP's feasible region and identified the optimal solution. It said the current objective function coefficients, or the C vector, is 3, 2. And it asked you to determine the range for which the second coefficient, or C2, can vary and this solution remain optimal. So basically the idea is what's going on is when the objective function has this iso-objective function line, which again we said that corresponds to negative C1 over C2, or you could have just sort of easily seen that we have 3 and 2 is our objective function coefficients, and negative 3 over 2 is the slope of my iso-objective line. Okay. What we're saying is, as I vary this 2, say that 2 becomes 1 or 3 or 5 or something, the slope of this iso-objective line changes. And you can see from the figure, as long as that slope remains within the slopes of these two constraints, which have slopes negative 1/2 and negative 2, the current optimal solution will remain optimal. If the slope becomes greater than negative 1/2 or less than negative 2, the optimal solution will move to one of these other extreme points. Okay, so we just set up our inequalities negative 2 less than or equal to negative 3 over 2 plus delta less than or equal to negative 1/2. So from this point, it's just algebra to finish out the problem. But what we can do is split that up into two distinct inequalities. Negative 2 less than or equal to negative 3 over 2 plus delta, and negative 3 over 2 plus delta less than or equal to negative 1/2. Okay, solving the first system of inequalities, let's see, then we'd have negative 4 minus 2 delta less than or equal to negative 3, and then that would give us 2 delta greater than or equal to negative 1. So delta greater than or equal to negative 1/2. Okay, working on the second inequality here, I'd get negative 3 less than or equal to minus 1 minus 1/2 delta. So I'd have 1/2 delta less than or equal to 2, or delta less than or equal to 4. Okay. Using these two pieces of information together, we get delta can range from negative 1/2 to 4. Okay. Almost done now. All we need to do is say delta we were measuring as the change in C2. So if the change in C2 can be as little as negative 1/2 or as great as 4, C2 was originally 2. So that means that C2 can be in the range of 1.5 to 6. And that's how you would have solved it.